Welcome to White Space. How big is TON 618 really? The black hole that swallows solar systems whole. Put this on in the background, close your eyes if you want, and let the story carry you. There are things in this universe that language was never built to describe, not because we lack the words, but because the scale simply refuses to fit inside a human thought. Black holes are one of those things. We know they exist, we've photographed one, we've heard the gravitational waves of two colliding, and yet the moment we try to grasp what they actually are, the math wins, and the mind surrenders. The question of how large a black hole can get has haunted physics for decades. And somewhere in a patch of sky near the constellation of Canes Venatici, more than 10 billion light years from where you're sitting right now, there may be an answer. An object catalogued simply as TON 618. A black hole so enormous that the physics we use to describe it starts to feel less like science and more like mythology. To understand why TON 618 matters, you first have to understand what you're actually looking at when you look at it. Which, to be clear, almost no one is, because finding it requires instruments most observatories don't have. What we detect from this object is not the black hole itself. Black holes, by definition, are invisible. What we see is the environment around it. The accretion disk, a vast ring of superheated gas spiraling inward at a significant fraction of the speed of light. Friction in that disk generates temperatures that dwarf anything achievable in a laboratory. The radiation produced is so extreme that it outshines entire galaxies, billions of stars rendered invisible by one object's appetite. This type of system has a name: a quasar. Short for quasi-stellar object, a label coined in the early 1960s, when astronomers first encountered these blindingly bright point-like sources of radio energy that refused to behave like stars. They had no spectral lines where they should have been. Their brightness was wrong. Their distances, once calculated, were staggering. A quasar is not a star. It is a feeding black hole, and it is the most luminous sustained phenomenon in the known universe. TON 618 was not always known to be a quasar. When it first appeared in a 1957 astronomical survey, it was catalogued as entry number 618 in a list of faint blue objects, presumed to be an ordinary star near the galactic plane. The catalogers had no reason to think otherwise. It looked like a star. It was entered and forgotten. That is where it stayed until radio surveys in the early 1970s flagged the region for unusually strong emissions. A star does not broadcast radio energy like that. Investigators looked closer, the spectral data was collected and analyzed. The redshift of the emission lines, a measure of how fast the object is moving away from us, which in an expanding universe translates directly into distance, placed this object at a remove that no star could occupy. This was not a local object, this was something from a completely different era of cosmic history. The light arriving at our telescopes from TON 618 left its source when the universe was less than 4 billion years old. The object we're studying is a relic, a fossil signal from a time before our solar system existed. The emission lines in its spectrum also revealed something else. The broad line region, the zone just outside the accretion disk where gas moves under the gravitational influence of the central mass, showed Doppler broadening, consistent with orbital velocities of roughly 7,000 kilometers per second. To put that in perspective, a bullet travels less than 1 kilometer per second. The International Space Station orbits at about 7,000 kilometers per second is not the speed that belongs in the terrestrial imagination. But it is exactly what you would expect if the gravitational source at the center of this system was heavy enough to force matter to move that fast, just to maintain orbit. Work backward from that velocity, factor in the size of the broadline region estimated from the quasar's luminosity, and you arrive at a mass estimate for the central black hole. The figure is approximately 66 billion times the mass of the Sun. That number requires a moment. Our own galaxy contains somewhere between 200 and 400 billion stars. Its central black hole, Sagittarius A star, weighs in at roughly 4 million solar masses. It is the gravitational anchor of the entire Milky Way, 200,000 light years across. The black hole at the center of TON 618 outweighs Sagittarius A star by a factor of more than 15,000. It is not in the same category. It barely seems like the same type of object. A black hole's event horizon, the spherical boundary beyond which nothing can return, scales with mass. At 66 billion solar masses, the event horizon radius of TON 618 is approximately 1,300 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun. Pluto orbits at roughly 40. The Voyager 1 probe, humanity's most distant object, is currently past 160. The event horizon of TON 618 extends to more than 1,000 times the Earth-Sun distance. Our entire solar system, every planet, every moon, every comet and asteroid in the Oort cloud. All of it would fit inside with room to spare. The event horizon of TON 618 is not astronomical in scale, it is galactic. This raises a question that does not have a comfortable answer. How does a black hole this massive come to exist so early in the history of the universe? The universe itself is around 13.8 billion years old. TON 618's light left when it was perhaps 3 billion years old at most. That means this black hole reached 66 billion solar masses in a time frame that conventional stellar evolution cannot explain. Standard black holes form from dying stars. A massive star exhausts its fuel, collapses under its own gravity, and the remnant, if heavy enough, becomes a black hole of a few to a few dozen solar masses. Even with generous accretion over billions of years, reaching 66 billion solar masses by that age is not possible through that route. The more likely explanation involves a different formation pathway. Instead of a star collapsing, an entire primordial gas cloud, millions of times more massive than any individual star, collapses directly. No supernova, no intermediate stellar phase, just an immense cloud of hydrogen and helium contracting until gravity wins completely. This process, known as direct collapse, would produce a seed black hole vastly more massive than anything born from a dying star. From there, in the dense, gas-rich environment of the early universe, it would feed rapidly. The conditions that allowed TON 618 to reach its recorded size were conditions that no longer exist in the present universe. That epoch is gone. The universe has expanded, thinned, and cooled. The era of quasars like this one is over, which brings us to a fundamental tension in the data. Quasars, including TON 618, are fundamentally a phenomenon of the young universe. They require enormous quantities of infalling matter to sustain their luminosity. They require matter to be shredded by tidal forces at the event horizon's edge, a process that only works efficiently when the black hole is not too massive. There is a theoretical threshold estimated by some researchers at around 50 billion solar masses, beyond which the tidal forces at the event horizon become too weak to efficiently shred incoming matter. The accretion disk becomes unstable, the feeding slows, the quasar dims. At 66 billion solar masses, TON 618 is already in territory where this mechanism should be breaking down. And yet, the signal we received showed a fully active quasar. The light output was extraordinary. The contradiction has not been fully resolved. One possible explanation is geometry. If the early galaxy surrounding TON 618 was dense enough with gas and dust, the dynamics of that infalling matter could sustain accretion even under conditions that would normally suppress it. Another possibility is that our models of the upper mass limit for black holes are simply wrong, built on assumptions that the early universe does not actually satisfy. We have derived these limits from observations of the present universe. The early universe was a different environment in almost every respect. Denser, hotter, more dynamic, saturated with the kind of material that black holes consume. Ton 608 is not the only candidate for the title of most massive black hole in the observed universe, but it is the most precisely characterized. Ici, Pont des Luz is the largest galaxy yet discovered, more than 6 million light-years across, containing over 100 trillion stars, and its central black hole has been estimated anywhere between 40 and 100 billion solar masses, but the uncertainty in that range reflects the difficulty of direct measurement at that distance. HD 121 plus 643 was until recently considered a strong candidate for the most massive directly measured black hole at around 30 billion solar masses. Each of these objects pushes the boundary of what we thought black holes could become. Each of them was discovered by accident, or nearly so. The deeper problem is not one of discovery, it is one of time. Everything we know about Ton 618 describes it as it was more than 10 billion years ago. That is not history in any ordinary sense. That is a completely different universe. In the time between when that light departed and when it arrived at our detectors, our sun formed and burned through a significant fraction of its fuel. Life appeared on Earth and ran through the entirety of its evolutionary history. Every human thought that has ever been thought, every civilization that has ever risen and collapsed, every piece of music and mathematics and engineering, all of it occurred in the interval between the emission and detection of that light. What Ton 618 looks like today, whether it is still active, whether it has grown further or stabilized or begun to decay, we cannot know. We are looking at a portrait of something that no longer necessarily resembles itself. And this is perhaps the most disquieting aspect of observational astronomy at these scales. We are not studying objects, we are studying signals. Ancient light encoded with information about a past state, traveling toward us through expanding space, arriving at our instruments and being decoded into numbers that we then call measurements. The universe at its largest scales is not something we can observe directly. We can only infer it from what reaches us. And what reaches us is always old. The observable universe currently extends about 46 billion light-years in every direction. As our instruments improve, that radius effectively grows not because the universe has expanded, but because we can detect fainter and more distant signals. Beyond the current boundary of observation, physics does not stop. Matter does not stop. Black holes do not stop. If Ton 618 exists at our observational edge, there is no principled reason why objects of equal or greater mass do not exist beyond it. We simply cannot see them. Not yet. Perhaps not ever. What we have in Ton 618 is a measurement. A number that arrived across 10 billion years and told us something was there. Something was enormous. Something fed on the early universe with an appetite that strains every framework we have built to describe it. Whether it holds the record is almost beside the point. The record exists somewhere. The universe scales up until it stops, and we do not yet know where that is. For now, Ton 618 represents something specific. The largest thing we have found, in the deepest place we can see, from the earliest time we can access. That is not the edge of what exists, it is the edge of what we know.